Hello, ladies and gentlemen. My name is Gorka Garcia Leiceaga, and on behalf of Robert, George, and myself, I present to you subsurface characterization using Ensemble machine learning. For decades, quantitative interpretation has been dominated by conventional methods, conventional workflows that are backed by theories and equations, backed by science. Such as Zoprits and bulk and shear modulus, Poisson's ratio, we've all heard of these. And conventional methods also tell us that anything that we get out of these 3D models, we can expect the seismic frequency content to mostly govern the resolution power of these models. And the work carried out in this study is an alternative to these conventional methods in order to successfully characterize a subsurface formation. The reservoir is an incised valley fill sandstone extending from eastern Colorado all the way through western Kansas into Oklahoma and into the Texas Panhandle. Using surface seismic methods poses a challenge because of the small scale heterogeneities in the target reservoir. So there's been a lot of other seismic data acquisition such as 3D VSP and crosswell seismic methods to try to get the detail required to successfully characterize this formation. In our study here, we are using surface seismic, and we have the full stack cube, which encompasses 3 wells. Wells A and B are encompassed by a pre-stack data set, which is what we'll be using in this study. But there's also well C, which is 3.4 kilometers away. Now, if you look at 2 things that I want to mention here, one is the seismic signal and how much better it is over at well C. You have more coherency in the reflections. When you get to wells A and B, you can see the quality of the seismic is just not as good. Also, the thickness of the reservoir at well C is significantly bigger than over at wells A and B. And also there's this bad gamma ray section, which I will talk about a little bit later on. Reservoir base here is indicated in red. So now this is the full gamma ray logs, and you can see this, there was a washout here, I guess. I'm not really sure, but it was a bad gamma ray. And I will again mention this later on. So in seismic reservoir characterization, we take the input data, seismic and wells, and we do inversion for rock properties. And once we have our rock properties, we can take those into the next domain, which is the rock property, or petrophysical property or reservoir property domains, such as gamma ray and resistivity and porosity. So it's like a 3-step process. Well, you have the input data, you have to go through inversion, and then you go to your petrophysical and reservoir properties. In this method, you don't have to do inversion, which is beneficial. So deterministic seismic inversion inputs, you have your seismic angle stacks. This is a pre-stack example for simultaneous inversion. And you have your your wavelets that correspond to each seismic angle stack. Then you have your well data, which also is used for building the low frequency model. And then you take all this information, you feed it into the inversion engine, and you get your acoustic impedance, VPVS ratio, and density. For ensemble machine learning, the algorithm builds a mathematical model that is based on the input data to make predictions. And it can be implemented without knowledge of theories and equations or conventional workflows that are usually backed by science. Now, I must mention, machine learning has been used in geoscience for a while now. There's, in 1D, you can predict missing logs and markers and lithofacies. In 3D, seismic processing companies are using it to better image faults and salt bodies and chimneys for their velocity models. and there's other applications of machine learning. And then when you have 1D and 3D for seismic reservoir characterization studies to predict elastic and petrophysical properties, which is what we're doing here. And just to note, I really haven't seen many, if any at all, successful petrophysical property prediction using machine learning. So I think this one will change that. So Ensemble machine learning, it makes use of several or multiple algorithms simultaneously to make a prediction that yields, in many cases, a lower error, and it's also less prone to overfitting. Trees are ideal candidates for bagging, which is a type of ensemble machine learning, since they capture complex structures in the data, and when you grow them deep enough, they have a relatively low bias. So this is a tree with showing multiple predictions, and then the final result is an average of the predictions. In this high-def rock property workflow, you have your seismic and seismic data, pre-stack. I've tried with post-stack and it doesn't work near as good. You have your hybrid model, which is kind of like your low-frequency model, but it has more frequencies in it, and I call it a hybrid because it also takes your seismic data, and then you feed this information into your Ensemble machine learning algorithm, and you get your single property that you're trying to predict. In comparison to the old deterministic or the conventional deterministic inversion workflow, you no longer need wavelets, and you're no longer simultaneously inverting for several properties. A little bit about the process. It can be carried out in both depth and time domains, and also requires pre-stack angle stacks or seismic partial angle stacks. And I want to say this, and hopefully at the end of this presentation you'll agree with me, but this method is able to double, even triple resolution. It also requires horizons to build the hybrid model, and optional dip and velocities to further constrain the hybrid model. And this is an amplitude spectrum of the data set. When you calculate it at the reservoir level, you're basically getting around 40 hertz. So just note that for later. So before we show the results, the machine learning model analysis, what I did was I used first well A to build the model, which is called the learning well, and then well B is the application well, which is the blind well. So here you have measured and predicted for the learning well, and measured and predicted for the application well. You see a significant, well, I wouldn't call that significant, but a drop in quality. Now, you also have here your cross plots between measured and predicted for both wells, and histograms. These are quality control measures. Now, I want to mention that the learning well is 100% accurate, the prediction. And this is something that some people may not understand because they don't have experience in machine learning, but where you use the data that you use to build your model, it better come out really, really good, because if it doesn't come out good in your learning well, then your application well, chances are it's going to be very poor there. So this is using well A for the model, and now this is using well B for the model, and using well A for the blind well, and you can see this issue here, which comes from that bad gamma ray. Now, this shows an image of a random line of the seismic full stack with the full bandwidth gamma ray logs displayed. So in this result, well A was used to build the model, And I would like to just mention that this is the segment of data that was used to build the machine learning model. Here's the reservoir here, the drop-in gamma ray. This is the hybrid model, so you can see more detail, but it's nowhere near as detailed as the log. And again, here's the reservoir. Now this is the high-def gamma ray result. And you can see a lot of detail now. Very nice match at well A, which we expect because this is where we built our model from. This is the data set we used to build our model. And now well B, this is the validation well, or the blind well. And this is again the poor gamma ray here. It's a little bit zoomed in, and now we have a filter of 120 hertz on the logs. You can see a pretty nice continuous formation. Matches really well here, matches really well here too. And like I said, 120 hertz on the cap on the logs. And the reason I chose 120 hertz because that's what I was using as my target frequency. Now these are the traces. The blue one is the log. The red one is the high-def gamma ray result. And this points to the drop-in gamma ray, which corresponds to the formation, target formation. And you can see here, it looks pretty good for the most part, except here you see a big mismatch, but the big mismatch comes from the bad gamma ray in this zone. This over at New Mexico Tech, which are they're the owners of the data. This is the geologic model that they have a lot of confidence in, and this is what they think truly represents their geology here. And when I saw this, I could just, I don't know, it just looked very similar to what I'm seeing here, so I just thought I'd throw that in there. Wells A and B are approximately right over here. So now we're zooming into the reservoir formation, and you can see here the drop-in gamma ray. Again, these have 120 hertz cap on them. And I think any geoscientist would have a difficult time identifying the top and the base, or interpreting the top and the base of this formation using this seismic line. When you take the high-def gamma ray, I think this would make it a lot easier. I think this result will give confidence to any decisions that are made based on this study. Conclusions. So I think the workflow has resolved the fine-scale features that conventional methods would not be able to reveal. And more specifically, we've got almost approximately 3 times the bandwidth of the input seismic data set. And like I said before, this is one of the things that makes this process so significant. Is the ability to give you so much more resolving power. The model was verified at a well location, a blind well location, which I think that's central to machine learning. You can't just have one well and move forward with that. I think you need to have something to validate. And this technology may encounter difficulties in areas where either rock composition or the depositional environment or general geology is significantly different between the calibration area and the predicted area. So I think that goes for pretty much any method. If you have complex geology, whether it's because of stratigraphy or because of structure, I think you'll have a harder time making predictions. I'd like to thank the United States Department of Energy's National Energy Technology Lab, and more specifically, I'd like to thank Multiphysics Technologies and DGB Earth Sciences for the support provided to publish this manuscript. And now I will leave the floor open for questions. Thank you very much.